Hello, everyone, and I will present you our work on the GNU Radio, GrGym framework we developed recently. This is a joint work with Sascha, Piotr, and Falco from Technical University Berlin, Germany. So motivated is our work by the big trend, what we see today. So we have wide range of applications using reinforcement learning. You might know reinforcement learning is a machine learning paradigm, which is already used for many years for designing sophisticated control algorithms for robotics. And recently, we also saw it's very successful in playing video games. The good thing is about reinforcement learning, you don't need any label data. You can immediately start training. How is it working? You see it on the lower left figure. We have a simple loop. So the agent, the reinforcement learning agent, observes the current state of the environment. Based on the observation and its policy, he selects some action he wants to execute. And then the environment in turn returns some reward associated with that action in a particular state. The agent again updates its policy based on the reward. So basically what the agent wants to maximize his reward. So in order to do so, he has to make the proper actions at the proper point in time. So OpenAl Gym, what is it? It's an open source framework, and you have lots of standardized environments already included, some algorithmic problems, video games like those presented here, some three-dimensional robotic problems. And the gym is basically allows you to develop reinforcement learning agents, algorithms, which you can compare because you have some clear defined environment, and with the same visual conditions, you can easily benchmark different solutions. The gym is finally some wrapper around those environments, and it offers a common API. And the application programming interface is quite easy. You have some kind of functions the agent can execute. And the most important one is the step function, right? So by calling step, the agent performs an action, and then he gets from the environment some observation and some reward. The good thing is about GrGym is the gym environment is that it's possible to integrate new environments as long as you are able to represent state and action as numerical values. The other framework, what we used here in our work is GNU Radio. I think you also heard about that. It's a rich toolkit which allows you to build software-defined radios. Basically, what you do is you design a flow graph where the vertices are signal processing blocks written in C++, and then you can wire them with each other, and then you have some data flow over the edges, and each block is then processing in real time the input data and create some output data. The interesting thing about GNU Radio is you have already you have a very active community, and you have already partially, sometimes even full implementations of different standards. Here we have some implementations of Wi-Fi, Zigbee, and also some partial implementation of LTE. And finally, the most important thing I would also say about GNU Radio is that you have the option to run your radio program either on real hardware, so you use some USLP, and then you can do over-the-air transmission, or you run it loopback in a fully simulated environment. That means that also the wireless channel is fully simulated in software. So now we come to our GrGym framework. So what is the goal? Why do we need it? So what we discovered in the last years is that modern wireless communication systems become very complicated. And also there are dynamic systems. If you look up in Wi-Fi standard, you see that the newest Wi-Fi standards have more than 100 parameters which you need to tune somehow. And what is even more complicated is that multiple of those parameters need to be tuned simultaneously. And we believe that conventional approaches to optimizing those parameters are, let's say, not promising, and we believe that new approaches are needed. And the idea is to use techniques from machine learning in general and reinforcement learning in particular. So this is our contribution here. We believe that, and the other, what we see from the literature is that more and more papers showing us that there is a gain if you use reinforcement learning to optimizing communication networks. So our goal is, with this framework, we want to give you the possibility to develop your own reinforcement learning-based solutions to optimize communication networks. And the goal is to make it easy and also to reduce the time it takes to implement it. And how we do it? The first idea is that we believe that you should, if you implement your reinforcement learning agent, you should start training it in a simulated environment before you go to the real world. So it means that you started train it in an environment where the wireless channel is also simulated, and then once you get some good results, you move to the real world. This is possible because SDR platforms gives us this flexibility, like GNU Radio, where you can quickly switch from simulation to real world. And this is also under the umbrella of transfer learning. So the idea is you can do also something in between. So you start learning in simulated environment, and then you use a pre-trained network, and then you can continue in the real world because, for example, the real world, the channel is more realistic. It's not so simple like in the simulator. Okay, so then we developed this GrGym framework. So what is GrGym? It basically it contains the following two components. On one side, GNU Radio, and on the other side, OpenAl Gym. And our main contribution is the design and implementation of a generic interface between the two frameworks. So at the end, what we want to have the possibility that any radio program you develop could become available as an environment in OpenAl Gym, so that you can then implement standard reinforcement agents, and then train it against such an environment. And the good news is it's not so much you have to do. So basically, if you assume you have a working radio program if written in GNU Radio, basically it's a flow graph. The only thing what you have to do is you have to make some slight modifications. So you have to add some additional blocks in the graph. I will show it in a moment. And those blocks are needed to connect this GNU Radio to our framework. And this is needed for lifecycle management, but also for the collection of observation data, reward data, and also the execution of actions. And the GrGym middleware, which is not visible for the user, is responsible for all the nasty things like the transfer and marshalling of the state from the agent to the GNU Radio back and forth. So you don't see it. So basically our framework has two parts, one a generic part, which connects the two frameworks, and one scenario specific part. And this is about, which is needed in order to describe the semantics. So for example, if you have an action is per se just a numerical value. And at some point you have to say, what is the semantic of an action? You have to say, for example, the transmit power level. And this happens in the scenario specific implementation. Okay, let's see how it works, the basic example. So the only thing, if you have a scenario which is already existing and you would like to use it because it's a scenario, it's a very well-defined scenario, and you want to design your own reinforcement learning agent, you have to write a configuration file. And what's in the configuration file, you see, you can have to describe whether the GNU Radio and the agents are on the same machine, or is it a remote? If you have two boxes, you have to communicate remotely. This is possible with our framework. And besides other configurations, the most important one, you have to select the scenario you want to use. Once you have it, then you can immediately go and write your reinforcement learning agent in Python. as you see here. And you see here, everything is standard Gym API. The only reference what you see that it's somehow connected to our framework is the argument in the make function call. You see here, the gym creates an environment which is GrGym. And from that point, our framework is started and everything happens which is not visible for you, and your agent can immediately interact with the environment. Now, the environment is a running GNU Radio program. And if you call the step function, for example, the most important function in reinforcement learning, you see that the step function is here on the left figure. It's somehow implemented by our framework, and lots of things happen here. And the most important thing is, if you call the step function, what the framework is doing, it executes the action you select here on the GNU Radio radio program. Then, depending on the configuration of the GrGym, you have a step duration, so there's some pausing. Then the reward is collected, again, using some information from the GNU Radio. And then it's the interesting thing is optionally, if you have a simulated environment where the wireless channel is also simulated software, here this channel is simulated. For example, you can here simulate mobility. And then the last step is the collection of the observation. And observation and reward are then finally transferred back to the agent, which then can make further decisions. So, but all the things happen in the framework and are not visible for the user. Okay, let's assume you're not happy with the scenarios we have already implemented, and you need a new scenario. Okay, for example, you have your own wireless protocol, and you would like to use reinforcement learning to optimize its operation. So here you have to follow the following 6 steps. So you have to set up your signal or network of GNU radio nodes. So you have to program your radio, your protocol in GNU Radio. Then you have, as I already said, you have to make some slight modifications to the radio program. You have to add some additional blocks to connect it to our framework. The third step is you have now to write the GrGym specific scenario class, which is a Python class, because this is needed to map the generic framework functions to specific functions. For example, here you are introducing the semantics. So if you say an action is not just a numerical value, it's a modulation encoding scheme to be used for the transmission, for example. Then, if you are done, you wire everything together with a config file. Then you have to write your reinforcement learning agent, which interacts with the environment using the standard Gym API. So everything is not visible for you. Then you train your agent, and then you can analyze the results. Those are the 6 steps. Okay, so as a proof of concept, we provide a specific scenario for GrGym. And the scenario is very simple. We have a point-to-point communication using wireless LAN, and we use the 8211 implementation from Blössl. And here we want to do what we call, what's also called closed-loop rate control. So we want to design a reinforcement learning agent which, based on the observation of the channel quality, the RSSI, makes the correct decisions on the modulation coding scheme to be used for the next packets. So if the quality of the channel is good, he will use high MCS. If it's bad, low MCS. And the reward, you need to somehow define the reward. It's the effective data rate. It's the number of successful bits transmitted in the last step. Yeah, and the good thing is you don't have to do so much. So we took this 8211p implementation. We added our additional blocks to connect it to our framework. Those are visible here with red. And as I already said, we have the option to use a fully simulated environment, and we did it here. So the transmitter and receiver are in the same flow graph, and they are connected over a simulated channel. Okay, so everything can run on a single box. You don't need any additional hardware. Yeah, this is our scenario. So now we come to the reinforcement learning agent. As I already said, he has to decide on the modulation coding scheme for the next packet transmissions. And immediately you can ask, why do we need reinforcement learning here? Yeah? Just use a table where from the signal strength you derive the MCS to be used, right? Should be a fixed table. But this is not the case because here in our example, the RSSI is uncalibrated. So the problem is we are getting the absolute signal strength, but because we don't know the noise floor, we cannot have such a table. And this is funny thing is now the reinforcement learning agent will learn how to map the absolute signal strength to the MCS. At the end, he implicitly learns the noise floor. Yeah, we implemented this. It's using some actor critic method. It's well known how it's working. So we have an architecture which consists of an actor. He makes the decisions. In our case, he selects the MCS. And then there is a critic which says, was it a good decision or a bad decision? He's doing some scoring. And as I already said, the scoring is a reward, and this is the effective throughput. Okay, so as I already said, we use this, our framework in simulated mode. So the channel was simulated. It was a very simple channel, a Gaussian channel. But every 100 milliseconds, we changed the RSSI, the mean RSSI value. This is in order to somehow simulate mobility. Okay, every 100 milliseconds, the RSSI was changed. And because we have such a simple Gaussian channel, it becomes possible to make further simplifications. For this example, to speed up the learning, for example, the observation, it's not needed to have the RSSI per subcarrier. You can simply calculate the mean over all RSSIs, and then the rest of the mapping was clear. So you see here, this is a neural network we used. We use the Keras API, it's a Python API. This is a simple neural network we used. Now let's see the results. So now we start the learning process, and at the beginning, when t equals 0, we see here the performance. On the x-axis, we see the RSSI, the observation, and on the y-axis, the reward. And what we see here is that at the beginning, the agent randomly tests, is randomly selecting different MCS regardless of the signal strength. So you see, even if the RSSI is very low, he still selects sometimes high MCS, which is not correct, right? You cannot transmit 64 QAM if you have very poor channel quality. So it's completely random. He's not taking the observation into account. But already after 570 episodes, you see he learned there are different ranges where you have to use different MCS. For example, for the low signal quality, you have to use QPSK. For the one in the middle, from 0.3 to 0.5, you should use 16 QAM. And only if the channel is very strong, you should use 64 QAM. So we were happy. So the learning performance is very good. So he was able to quickly learn to select the proper MCS given the observation. So the final question is, so far the channel was simulated. The question is, can we go to a real wireless channel? Just remove this simulated channel, use SDR, and do over-the-air transmission. Unfortunately, you have to be careful because in such a scenario, the latency of our framework is an issue because collecting the observation, executing the action takes time. In our case, around 1 to 3 milliseconds. And this is already an order of, some value which is can create in a mobile scenario some problems. You see here in the lower right table, if the mobile is moving is 5 meters per second, we have a distributed setup, so the agent and the GNU Radio on two different computers, running on two different computers, then what we have here, the problem is that in 27% of the cases, the agent will make a wrong decision because he makes it on outdated observation. So what from the results, what I showed here, you have to be careful if you run it in a mobile channel, because here latency might become a problem. Okay, I conclude my talk. I presented GrGym framework, which is simplifying reinforcement learning for solving problems in areas of wireless communication systems. It is based on OpenAl Gym and GNU Radio frameworks. And for future, we plan to add more custom scenarios, for example, support some interesting problems from ZigBee and LTE. We want to also think about how to improve the network latency so that it becomes possible to run over real channel, even with high mobility. Yeah, and we hope that there will be some research community around that. All the code you can find on GitHub is open source, and we are now working on improving the software. Thank you.